Just thought I would record a short video on factors that affect rate of reaction just to help you. Here's the list of factors. The first one is catalysts, which we know are a substance that's added to a reaction to alter the rate of reaction without being used in the reaction itself. That means that it can be removed at the end of an experiment chemically unchanged. So although physically it might look like it's changed slightly, chemically it's the exact same. Second one is particle size, so that's how big or small the particles are. Concentration, temperature and nature of reactants. So first things first is we need to know our definition for catalysts. Lots of people off the tip of their tongues will automatically say catalysts speed up the rate of reaction, when in actual fact some catalysts will actually slow down the rate of reaction. For example, if a reaction is almost explosive, that's going to happen instantaneously, really fast reaction. Obviously, if you want to see the reaction working, you need to slow it down. So although they might be rare, 99% of your catalysts will speed up the rate of reaction, some of them will slow it down. For that reason, the real definition for cert chemistry is that they alter the rate of reaction, because it can go either way. You then can have catalysts that actually have a negative effect or that slow down. These are called inhibitors, so they kind of stop reactions essentially. These general properties of catalysts are really important. We actually should number these 1 to 5, and you definitely should take them all down your copy. This comes up almost every year, either as a short question, question 4, or as a question 5 a part. If it comes up rate of reaction as a long question, it might come up as a part of that question. List 3 properties of catalysts, etc. So we know that they are recovered at the end of a chemical reaction chemically unchanged. They're very specific, so a catalyst is like a rubber glove. It will fit onto the hand, it doesn't fit onto the foot, so it'll work for one chemical, it will not work for another. Only small amounts of catalysts are needed, so we usually just add like the tip of a spatula, tiny amount. This question we actually won't make much sense to us until we do the chemical equilibrium chapter, but catalysts help equilibrium be achieved more quickly. They do not affect the position of equilibrium. And lastly, the action of a catalyst may be destroyed by catalytic poisons. Second one we're going to look at is particle size. So every time I teach this, we use this plain old example of cooking potatoes. So the greater the particle size, the slower the reaction will be. Very simply put, if you have large potatoes like this and you put them on the boil, you might be expected to wait 20 minutes for them to cook, 25 minutes for them to cook. If I decided then to take those exact same potatoes, the same quantity, and chop them all up into tiny pieces like this, they'll cook much faster. What is the difference? So I've just actually went and cut one for myself. Here we have our potato. This is a potato, roughly the exact same size, This is our original potato. If I was to decide I'm going to bake that, I'm going to just place that into the oven exactly as it is. This will take up to 30 or 40 minutes to actually soften. I'm not a home ec teacher, so I'm just guessing, but we'll say it'll take that time. The exact same size potato I've just cut up, as you can see, into all these lovely little wedges, So if I was to place all those little wedges into the oven, they'll cook much faster because they're much smaller. The smaller the particle size, the greater number of surfaces they have. For example, this little wedge has one surface, has another surface, and it has all this edge all the way around. So because there's so many surfaces, we say it's a greater surface area, and all of these collectively have a much greater surface area than this potato, which essentially only has one surface the whole way around. So the greater the surface area, the more space or area there is for the heat to actually penetrate into the potato, and hence it will cook much faster. This one is a large particle size, small surface area. This is a smaller particle size, much larger surface area. So looking at this, we have the greater the particle size, for example our potato, the slower the reaction will be because they only have a small surface area. The smaller the particle size, the faster the reaction will be. Every time it's really handy to think of our cooking potatoes for that one. Then this is an example that comes up sometimes in the book, and it might come up as a short question. It says, we're using marble, which is our calcium carbonate, and you're placing it into hydrochloric acid. Now, it says dilute hydrochloric acid, so we're going to assume it's 0.1 molar. So we've 0.1 molar hydrochloric acid. I take large, big lumps of marble and I pop them into it. What's going to happen is it produces bubbles of carbon dioxide. Okay, now I could start that experiment once. With the large marble chips, you will see a small few bubbles of carbon dioxide being produced in, say, 30 seconds. Then I might decide to redo this experiment, rinse out everything, start again, but instead of using large lumps of marble chips this time, I'm going to use powdered marble chips. So it's the same amount of marble chips, but I'm going to use a pestle and mortar and grind them down until they're a really fine powder. I now add my fine marble chip powder into the same concentration of hydrochloric acid, and in the first 30 seconds I'll expect to see loads and loads and loads of bubbles. So what's happened there is a much faster rate of reaction in the same amount of time with the powdered marble chips as opposed to the lumps of marble. Okay, so it's a little bit cut off at the bottom, but it says if the same volume of dilute hydrochloric acid is added to the same mass of powdered calcium carbonate at the same temperature, there is a large increase in the rate of reaction, i.e. a large increase in the amount of bubbles produced in the same amount of time. And here's just two little graphs to show that. So on the iPad, for some reason, my little arrow turns into this symbol, but that's the arrow. So marble chips and hydrochloric acid gives us calcium chloride, water, and carbon dioxide. This is the reaction as you would expect to see your results as the reaction continues. So as the time increases here, you can see the small marble chips lose mass, or i.e. create carbon dioxide gas very, very quickly initially, and then the reaction begins to level off. Whereas the large marble chips do not lose their or do not create carbon dioxide as quickly at the beginning, and then the reaction levels off. Okay. Now, next thing we're going to look at is concentration. So factors that affect rate of reaction, concentration is another one. So it'd be very clear to you if I had 3 different glasses of my Wadi Orange and they were all of different concentration. You'd be able to tell me very quickly one of them is very dilute, one of them is very concentrated, just by looking at the colours. If you could actually see into those glasses and you wanted to see all the different particles, I'm going to really loosely draw out 2 glasses here, okay? The first glass here of my Wadi, these are all the little atoms. Okay, and then the second my Wadi, this is the atoms. Very easily, by looking at the 2 of them, you can say, well, this one's a lot more concentrated than this one. Throughout this entire chapter, there's 2 really important keywords we need to keep in the back of our head all the time, and they are effective collisions and activation energy. Okay, which we know is EA, like that. Now, what I'm always thinking about is effective collisions and how many of the atoms actually reach activation energy. If I had a glass that looked like this one, and these are all my little atoms constantly moving around in the glass, I would say this is a concentrated substance. This one here is quite a dilute substance, okay, or we'd say low concentration. All these atoms here are moving around all the time in the glass. Is it likely that they are going to collide with one another? Yes, because this is a very concentrated solution. There's loads of atoms there, so they're constantly going to be colliding with one another. That means that a good quantity of them is probably going to have enough energy to reach activation energy and produce a product. Whereas over here, if I have very few little atoms spinning around in this huge big glass, the chances of them actually colliding is quite slim. That means that they're never going to reach activation energy. So with a greater concentration, you're going to see more effective collisions and activation energy being reached, meaning you're going to have a faster rate of reaction. Looking at this experiment here, you can see we have a magnesium ribbon in 1 molar hydrochloric acid. Magnesium and hydrochloric acid will react to produce hydrogen gas here. With all rate of reaction experiments, you need 2 things to keep in mind all the time. Rate incorporates time, which means you absolutely need to draw a stopwatch in your diagrams. Secondly, it's usually the amount of something being produced per unit time. If I'm measuring in this example the amount of hydrogen being produced, that means that I absolutely need a graduated cylinder or have lines here on your diagram to show that you can actually measure a quantity. If I drew a test tube here instead of a graduated cylinder, you'll lose marks in the Leaving Cert because you're not actually able to measure the quantity of hydrogen being produced in a certain unit of time. So, magnesium and 1 molar hydrochloric acid is producing hydrogen gas there. If I was to repeat this experiment again, instead of using 1 molar hydrochloric acid, I use 10 molar hydrochloric acid, 10 times as concentrated as this acid. I would expect that reaction to happen 10 times faster. Why? Because in my reaction vessel, I have a lot more hydrochloric acid molecules, therefore a lot more collisions, more likely to have more effective collisions, more particles reaching activation energy, therefore more product being produced at the end. Okay, so we see here magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. You can see here a 1 molar hydrochloric acid solution will have a very fast rate of reaction initially, meaning in a short space of time you have a huge steep slope here, huge amount of product being produced. Then the reaction begins to level off as maybe all of the hydrochloric acid is used up. Here this student has repeated the experiment using 0.5 molar hydrochloric acid, hence exactly half as concentrated of a solution, and you'll see this slope is exactly half as steep. Therefore, the more concentrated a solution, the faster the rate of reaction. The more dilute a solution, the slower the rate of reaction. The fourth factor we need to think about is temperature. So everyday example, very easy to remember. You go out to the shop and you buy your fresh strawberries. Where are you going to leave them? In the fridge. If I leave them out at room temperature, okay, nice warm room temperature, they'll begin to go off a little bit faster. If I place them in the cold fridge, they take a much longer time to go off. Bacteria or fungi growing on the surface of this this strawberry is going to react very quickly in hot temperatures, ideal temperatures for the fungus to grow. If you put it into the fridge, it's going to react or move much slower, less effective collisions, less reaching activation energy, hence it slows down the rate of reaction completely. Okay, so we see here the lower the temperature, the slower the rate of reaction, the higher the temperature, the faster the rate of reaction. The last factor to be considered is nature of reactants. Okay, nature of reactants. So we see here you can have instantaneous reactions. That means that they happen instantaneously or it happens very quickly. So an instantaneous reaction will be almost explosive. It says reactions that do not involve bonds breaking but merely the coming together of oppositely charged species in a solution, they're fast at room temperature. So if, for example, you have something like H plus and Cl minus, plus and a minus are going to come together very quickly, hence that reaction is going to happen instantaneously. There's no breaking of bonds or there is forming of a new bond, but there's no breaking of bonds here in preparation for producing a product. They simply come together, one collision, and you've produced a new product. So that's a very fast reaction. However, you can also have reactions that involve covalent bonds, okay, so substances like molecules that are already bonded to something else. And these are much, much slower at room temperature.